you're comfortable, then we can just move on. All right, so this is Chemistry Unit 2, Paper 1 for May, June 2017. Right, so let's look at this. The volatility of organic compounds depends on the strength of intermolecular forces present. Right, which of the following compounds would be the most volatile?
C.
C. C is a alkane. Alright, C is an alkane.
I remember my sister saying something about like when there's a brand.
Yeah, the more
I don't remember.
branch it is, I
It
think
makes
the
it more.
makes it more volatile for real. Um, why not an alcohol? Though I'm just asking, why not an alcohol?
Because it's polar. Has strong bonds between them.
Okay, so volatility speaks this ability to what?
Escape into the gas state from liquid, I guess.
Change state or
Change state. Well,
Yeah.
change state is enough, right? And if it's non-polar, then it won't generally stick together. But it really depends on what it's mixed with. To be very honest, organic compounds depends on the volatility. I think the volatility generally speaks to it within aqueous environments. So I think that should be fine. If it is in an aqueous environment, then that would be fine. Alright, aqueous obviously, meaning water is present. Because if it's in water, then it's non-polar, that means it would be the most volatile. Alright, and we looked at the graphs of for like Rhodes law and stuff like that, and we'll understand how these molecules work based on molecular structure, right? Our volatility works based on molecular structure. Right, now looking at this exact repeat, hydrocarbon said has a relative molecular mass of 84. Right, when 0.1 grams of Z was burnt in oxygen, 0.316 grams of carbon dioxide, and 0.128 grams of water were formed. The empirical formula of Z is?
I think I got B for this one.
Alright, it is B. Because we're supposed to get what? What are we supposed to get for the C6H12? And the empirical formula should be that. After you put it in simplest whole number ratios, the molecular formula should be C6H12. Right? So one other thing you can use to get this, we know that the molecular formula, the relative molecular mass should be 84. So this is the only one that is 84, and then the empirical formula is this. So if you see that the mass is 84 and you choose an answer that is not 84, right? I hope that you do not require a resit next year and we just pass and go through. Alright? So let's move on. Number 4. In the reaction between ethene and bromine, which of the following statements about the reaction mechanism may be true?
D, all of the above.
Alright. So carbocation forms in the rate determining step. That is true. While we're looking at ethene and bromine, that's fine. Dative covalent bonds form between bromide ion and ethene. That is true as well. It would be dative. And because it's a carbocation, so it has to be dative. And then heterolytic, it has to be heterolytic fission as well. Alright, so, yeah, it has to be heterolytic fission. So D would be the best answer here. Alright, so let's move on. The correct IUPAC name for the compound is?
A, 2,2,4 trimethyl pentane.
Alright. So everybody got this, right? Just to make sure everybody following. Everybody immediately get this.
Yeah, I got it.
Alright. There's nobody here that don't understand how to do this. Because they can literally just give you anything and ask you to name it. So I want to make sure that you know how to name in case any new questions come. Everybody's fine?
I'm good.
yes, sir.
Alright. So which of the following reaction mechanisms occurs between benzene and concentrated nitric acid and sulfuric acid?
Sir, wasn't it A, sir? 2, 2.
Wait, what? Oh, 2, 2. Oh, I just saw it. My bad. Alright, it's supposed to be 2, 2, right? So if we name it to give the constituents the lowest, 1, 2, 3, 4, 5 will be 2, 2 dimethyl. 2, 2, 4 trimethyl pentane. Alright, so which of the following reaction mechanisms occurs between benzene and concentrated acids like these?
A.
Alright, so A, and that would be which reaction is it synonymous with?
Nitration.
Of benzene. Wonderful. Right, so the product of the reaction above is, so we have this alkenyl phenol, right? So we have this type of, well, it would be a benzyl group plus this. So what type of what would be the product? Not asking the type of reaction, but product.
B.
D as in dog. Alright, so we're looking at this. Would it be D? Let me check.
I said B.
Oh, B as in boy. Alright.
One else said B.
Okay. So let me check. The double bond will break. Alright. So we're not looking at that. And we'll understand that Markovnikov's rule will govern this as well, right? Not so much, to be very honest, but there will be a different rule that governs it, to be very honest. We don't have to know those yet. 8. Diazonium salts are useful in the analysis of aromatic compounds. Which of the following compounds can be prepared from a diazonium salt? Diazotization, right, to create the salt. Alright, and then we have the coupling reaction to create our di, right? So C would be the answer. Hydrogen cyanide can be added to ethanol, but not to ethane because?
E.
As in?
Cat.
Okay. Alright, so ethanol is more susceptible to neutrophilic attack than ethene. And we would know this why, right? We know that within ethanol we have that aldehyde group dragging electrons closer to the oxygen, creating a more positive bond here. So, well, a more positive interaction here, or, state of affairs, I guess, right? Allowing for some amount of nucleophile to have the greatest impact for nucleophilic attack, right? So we have that there. So let's look at, I think this repeat, the organic liquid Z is most likely. So we know that Z can liberate carbon dioxide, right? And we know that it creates HCl with thionyl chloride. So what would be the best answer?
D as in dog.
D as in dog. Alright. So by the fact that it can liberate carbon dioxide generally, right, we would understand that it cannot be a carbonate. Who would have put carbonate in their right mind? Can be an alcohol, can be an carbonate, right? Well, it could be an acyl chloride technically, right? But the acyl chloride won't generally react with the thionyl chloride to give us the white misty fume. So note that as well. Right, 2-hydroxy-2-methylpropanoic acid can be formed from propanone in 2 steps, X and Y, as illustrated below. So wonderful steps. What is that? Oh yeah, that makes sense for real. Alright, so that makes sense. So which are the following steps about these steps? Well, which are the following statements, sorry, about these steps is or are true?
All 3 are true.
Okay, so step X involves neutrophilic addition, so we know that we're going to be creating our cyanyl group on it. Aqueous potassium cyanide is the reagent, wonderful. And step Y involves hydrolysis, which is, give me a moment, let me look at something here. It involves hydrolysis. Alright, okay, it can involve hydrolysis, so yeah. So we're cleaving the nitrogen off of the compound to add our hydroxyl group. So nitrogen is left, right? And we're adding water, right? So nitrogen is left and hydroxide is added. Right, so it's a type of elimination. Right, 12. Nylon 6,6 can be made by the condensation, polymerization of these 2 substituents. The repeating unit is?
B.
As in?
Boy.
Okay, I asked you guys to say as in just to make sure, because when you say it, I'm not too sure whether or not you're talking about B or C, or it sounds really the same to me. Alright, so we have that. Everybody understands why we have B. Thumbs up if everybody understands why. If you understand why. Wanna make sure we know. Alright? So, alright, so let's move on. 13. Which of the following statements is not true of addition polymerization? This repeated, right? What's the answer?
Boy.
Alright, so polymer is readily. Alright, so we have that there. The butanol, well, when butanol is dehydrated in a suitable piece of apparatus, the product is.
I have a question.
Go ahead.
I'm built one in.
What's the question?
What's the difference between butene and butene?
Okay, the difference between butene and butene, I don't think there's a general difference. Because, to be very honest, right? Okay, hold on. Yeah, okay, hold on. Let me look at it. So, butene, right? So, we're gonna have bute, right? Just drawing the carbons like that. We're saying that it's but1-al. So, it has to be an alcohol. Right, when this breaks, the sp3 hybridization, yes, breaks, right, and then allows a free p orbital to be established, right, and it's going to actually take a hydrogen as well from the other carbon. So we're gonna have two p orbitals open for the overlap here. Agreed?
Agree.
All right, so it's gonna be here. So we have to give the alkenyl group or the double bond the lowest number because it takes priority over all sigma bonds, right? So we have carbon 1, 2, 3, 4. So it has to be carbon 1, right? But what is the difference between butene? I think butene is more vague, right, compared to but1-ene and but2-ene, because it could be but1-ene or but2-ene. But the fact that they said but1-al, it has to be but1-ene specifically, if you get what I'm saying.
Yeah, that makes sense.
Alright, so I think it's specificity they're looking for. But I don't think butene should be wrong, so I think they probably should replace it. But I guess it's just trying to make the question a bit harder. What would be observed when the aqueous bromine is added to the following compound? Phenol. What would be the answer?
B.
I would guess it's B as in boy.
Oh yes, B as in boy.
Alright. So the
Yeah.
color of bromine would be discharged. So we know that every single time we have a halogen gives off color. But when the halogen is added to a compound, it loses its color. We know that already from fifth form. Alright. So we know that the color is going to be discharged, and a white precipitate along with an antiseptic smell will be arising.
Wait,
Go ahead.
before you. So there was another question pretty similar to this one, but instead of the phenol, they had 2,4,6 tribromophenol. But they said what would be observed when aqueous bromine was added to 2,4,6 tribromophenol. Would the answer be A in that case?
There would be no visible. Yeah, true. Because we know that the hydroxyl group would be an it would be a R through para projecting group, right? So we'll only connect to the O and the P, not the M generally. Even though some can connect to the M, right? Based on its low probability, we call it an OP director, right? So it's going to be RD occupied, so nothing really much can happen if the molecule is RD occupied, giving full steric hindrance and stability. So I don't think anything should happen. Things may be able to happen, to be very honest, depending on the rest of the circumstances, but you won't be able to see it based on the fact that aqueous bromine, right, for sometimes it may be it won't be visible sometimes, right? But based on the fact that there would be no addition or subtraction theoretically, right, there should be no visible reaction, right? If there's a color there, the color will remain. If there's no color there, the color won't change, right? So we won't be able to see anything. Let me just add somebody to this. Oh, it's Cheyenne. Alright, so I don't want to mark up the paper too much, alright, give this screen a second. I don't know why it blacked out a while ago. Alright, it's okay. Alright, so number 16 refers to the following diagram, which represents a paper chromatogram of food dyes obtained by using water, right? Water is polar as the solvent. A spot on the sample was originally placed at Z it contained the component X and Y. Alright. So what do we know of X and Y? What do we know regarding these components? Remember that our solvent is polar. What would be the answer?
D.
Yeah.
D. Okay, sounds like D as in dog.
Yes.
Alright, so Y is more strongly absorbed to the paper than to X, so it shows why the difference is, well, in distance is shorter, so it makes sense. And Y has a smaller R, well, obviously. Alright, so we would go with that. Alright, so that makes sense. That's fine. Alright, number 17. Species which absorb light in the UV region have...
C.
Has to have unsaturated bonds and non-bonding pairs of electrons. We don't deal with saturated bonds around here. Because in order for there to be, I want you guys to understand it, right? We know that the transitions to happen are non-bonding to sigma star, non-bonding to pi star, right? And pi to pi star. Now, if it is a saturated molecule, there is no pi bond, so how are you supposed to have to pi star? Think about that. So it has to be unsaturated. And then it has to have some amount of non-bonding electrons for non-bonding to be going to sigma star and pi star. Right? So it makes sense when you connect everything. Like why one shouldn't generally be the answer. It shouldn't be only consisting of saturated bonds. It can have saturated bonds, but it shouldn't only be consisting of it. Right? But the main characteristics, right, would be unsaturated bonds and non-bonding pairs of electrons. A student used gravimetric analysis to determine the percentage of mass of calcium in chalk. Right? The student weighed 2 grams of chalk and dissolved it in HCl, then added excess ammonium oxalate to precipitate the calcium ions. The precipitate was filtered, dried, and weighed. The percentage by mass was then calculated. It was found, however, that the result obtained was lower than expected. So what do you think happened here? Which of the following sources of error could possibly account for this difference?
Hear me out. I'm thinking between B and C, but if you're saying they added excess, could incomplete precipitation still occur if they said they added excess amount of ammonia oxalate?
Okay, excess will increase the chances of perfect, well, not a perfect, right, of complete precipitation, right? Because incomplete precipitation will occur when the common ions, well, it doesn't have to be common ions, never mind that, right? When the mole ratio is not like at its optimum, right? Where, remember how limiting reagents work, right? If it's in excess, then the limiting reagent will not exist. There would be nothing limiting the production of the precipitate, right? So there will be enough ammonia for every single molecule to react to create the precipitate. So I think if it's in excess, it kind of rule out the possibilities of incomplete precipitation being it. Although incomplete precipitation can be an answer, multiple choice questions look for the best answer. Alright, so I'm not saying that incomplete precipitation is impossible. It could be it. But is it the best answer? Based on the fact that we
We'll
have
go with B.
excess.
Everything
Alright, so
waves.
B. Weighing, right? So we're saying you have a lower mass than expected, right? Incomplete drying would allow water molecules, right, a hydrated complex to remain, and that will increase the mass. So it shouldn't be the answer. And other ions precipitating from the solution, right, that would add to the mass, not lower the expected mass. So B should be the better answer, right? Let's look at this. We did this question already. Treatment of 10-gram sample, well, a 10-gram sample containing a chloride salt with excess silver nitrate solution produced 8.08 grams of silver chloride. Right? I think we went through this entire thing in the first like 5 to 10 minutes of the video I uploaded for the 2021. I went through the entire thing step by step. Right? So which of the expressions can be used to calculate the percentage of chloride in the sample? What did we do?
Yes, and boy for this one, 19.
Alright. So we're going to have the mass of the chlorine divided by, well, the molar mass of the compound times the mass of the given, right? Well, not the mass of the given, the mass of the sodium chloride given, right? Well, produced, I should say, right? Divided by the mass of the sample itself, right? And when we times it by 100, we should be able to get the percentage of chloride ions, right? And because the 1-to-1 ratio, the general mass of the chloride, the silver chloride will be the same mass of the chlorine, based on the fact that it's a 1-to-1 ratio within the salt itself. If we remember KSP, we should get it. Go ahead. How we know that silver chloride will give us silver plus, in this case, silver is in its first oxidation state, and then within silver chloride generally, and we have, why depend not writing, it's flopping my show, I can't believe this is embarrassing. Alright, so yeah, so you know it would be a 1-to-1 ratio based on the dissociation, which is an equilibrium, right, of these two. So that means that the mass of the overall molecule would be the same mass of that and the same mass of this, right? So it should be fine. 20 different regions of the electromagnetic spectrum have different energies. Wow, who would have guessed? Which of the following equations justifies the criteria for dividing the electromagnetic spectrum into regions according to wavelength? Here, F is frequencies. V should be frequency, but they show that F is frequency here. So which of the following equations justifies the criteria for dividing? Go ahead.
D as in dog.
Alright. So some persons will immediately go to the only equation in this entire section that they gave you, right, for this type of thing would be E equal hc over lambda. And that calculates the energy in accordance with what?
With your wavelength.
What is Planck's constant? What does Planck's constant speak to again? Unit 1. If you can go back, what does it speak to? Would be that times the speed of light.
What is Planck's constant?
Yeah, like it's a number, you know, right? But what does the number speak to? For example, Avogadro's number, we know what it is, and we know what Avogadro's number speaks to. But what does Planck's constant speak to?
Actually, I can't remember it.
So I want you guys to go back and look at it. Just have a brief look at it and what it speaks to, right? We can't just know the number. We have to know the significance behind the number, alright? So we have that there divided by the wavelength specifically. So it shows the energy, right, that may be occupied or may be, you know, present or may be related to a specific wavelength, right? So using the different energies, we can divide them into different spectrums based on, well, different sections based on similar energies, right? So we have that there. Go ahead. Somebody has their hand up, I believe, or somebody asking a question. Let me check. I do see. Oh, go ahead, Kayla.
Oh, yeah, I got disconnected. So for number 18, I was asking how you got B.
Okay, so we're seeing for number 18, right, that, okay, we're seeing that the results obtained were lower, right? That means it can be incomplete drying because water would be still present, so it would increase the mass, not lower it, and other ions precipitating from the solution would increase the mass, not lower it. Now, there are chances of incomplete precipitation, but we're looking for the best answer here. Based on the fact that we have excess, right? Or is it excess ammonium oxalate? We have excess ammonium present, well, ammonia based off of dissociation, right, in the solution, right? So generally here we won't see a limiting reagent, if we remember the concepts of limiting reagent, right? So it is in excess, so that means that there is enough to go around for a complete combination of the atoms for precipitation to occur. It's not I'm not saying that incomplete precipitation is impossible, but it would be really least likely in this situation. So I think that the most probable error would be error in weighing, because there's enough ammonia to precipitate out, right? So I think error in weighing would be the best one here. Do you think C would be the better one?
No, B makes sense.
All right. Okay, and we got that. I explained this number 19 with literally the written equation and everything in the first 5 to 10 minutes of my video on 2021, right? We got that, and 20 we're looking at we're looking at energy is equal to Planck's constant and speed of light divided by the wavelength, right, to divide it into different regions. Based on energies, similar energies will allow them to group into different regions, right, based on wavelength, right? So we have that there. So we know that different wavelengths correspond to different energies, and we know all of that from unit 1 when we're talking about electron excitation and photo excitation and stuff like that, right? And we know that the discrete energy levels come from the wavelength, right, or it can be due to the wavelength of light. So based on the energy, right, that is given by a specific wavelength, we can divide the spectrum into different sections, right? So why we have, for example, X-rays and stuff like that, right, it's based off of the wavelength as well as the frequency itself. Well, as well as its frequency, and that will give a specific energy. So I think E equals HC over lambda would be the best thing we use. Go ahead. Alright, so E equal MC squared, everybody knows that one. Alright, so 21. Which of the following materials are commonly used stationary phases in chromatography?
Days and dogs.
Are you sure? Are you sure about that?
Yeah.
Yeah.
B as in, oh, there's a dog. Alright, so we have cellulose, alumina, and why did I say like that? Alumina. Okay, alumina and silica gel. Right? Okay, so the complex ion. Somebody name this one, please. I'm joking, you don't have to name it. Has a molar absorptivity of that, right? Oh my, I love these questions so much. So we know that we have Beer-Lambert's law. Somebody tell me what Beer-Lambert's law is. The concentration of solution gives that. So we have to look at this. So what is Beer-Lambert's law?
That the
Equation?
absorb
That the
oh
absorbance is equal to
the molar absorbivity
epsilon.
times yeah times the concentration times the path length in centimeters.
Wonderful. Right, so we have the molar absorptivity, which would be 7.0 times 10 to the third power. Right? The units are all the same, so you don't have to watch units in this one. The units are all the same with every answer. Right, so we have that, and we timesing it by what? We have the absorbance. Wait, let me see. Which gives an absorbance of that when measured in what are we calculating here? The concentration, right?
Yeah.
Yes.
Alright,
With
so we're going to have X here, and we're going to have the concentration, which is 2, and it is in cm, so it's fine. So I think absorbance may trick up some persons. Some persons probably are going to use 4.2. Please don't use that. You have your molar absorptivity, right? Generally, right? What's your absorbance though?
4.2.
4.2. So don't use it as molar absorptivity. Some people mix that up. So absorbance, it would be equal to the absorbance 4.2. Let me put it at the end. Equal to 4.2. So x would be equal to what? Make x the subject of the formula. Or the equation, sorry. What?
Right.
The over here.
Repeat?
I think over here.
So C would be A over epsilon
Over
L.
epsilon L. Yeah.
Alright, so 4.2 divided by 7.0. Wait, 7.0 times 10. Sorry about that. Oh, it looks weird. Times 10 to the third power. Alright, and we times that by 2, right? So what's the answer for this equation? Well, what's the answer here? What's X?
C.
C? Did
Three
everybody get...
times.
Alright, did everybody get C? Any different answers? Cause we're moving, you know. Alright, so moving. 23. In the infrared spectrum of an organic compound, a strong band is observed at 3000. Alright, that wave number. The most likely explanation is that A strong band. So the band specifically around 3000, right? The band that come down so. I mean, it looks weird, but it's strong, right? At around 3000. So what's happening? What does the band speak to? Do we know how the graph looks? We have the wave number here, and we have what? Absorbance or transmittance? On the y-axis, what will we have? Absorbance or transmittance? How we know the difference between I naught and I, right? So, what would be on the y-axis? Absorbance or this transmittance? Alright, we don't know. Alright, so we don't know. So let's just write X there. We don't know. But what would be the answer for this since we don't know?
A.
A. So radiation is absorbed, is absorbed and causes CH bonds. Okay, do you think the wave numbers have anything to do with this question?
No, I don't think so.
Alright. So okay, alright. Bonding electrons absorb radiation are excited. So I'll go ahead, what you saying?
I was asking it, wouldn't it mostly be OH that absorb in that range that I mentioned?
It could be around OH, yeah. But I don't see a suitable answer for that. Because I don't think decomposition will occur. Protons absorb what now? Radiation is. I think this is kind of true. That's fine. Bonding electrons. There's no type of electronic promotion within IR. They're chilling now. When you go into IR, our IR molecules are chill. They just have smooth vibrations, right? They don't care about that promotion business. They just vibrate in place. Right, so I think that the best one may be around A, based on the process of elimination. Right?
You were asked before what would be on the y-axis. If it would
Yeah.
be absorbance. No, absorb. Yeah, you said absorbance or transmittance.
Yeah.
Would it be?
Wait, I didn't hear what you said. I think you muted your mic quickly, so it cut off. What you said?
I was asking what would be on the the y-axis. Sorry, would it be the transmittance or the absorbance, or would it depend?
It would depend on the graph well, some graphs would have
Yeah.
it differently, for real. Right? But usually we're looking at absorbance. Right? Is absorbance you're looking at? So the amount of energy really absorbed around those regions will tell us. So the wave numbers kind of speak to that. Right, they tell a story. Okay, which of the following regions of the electromagnetic spectrum best matches the wavelength ranges of P, Q, and R? So basically we're wondering what comes before and after these. Right, so and we're looking at the frequencies. You see them here now, right? So what's happening here? Lower frequency. What is the relationship between frequency and wavelength?
Longer wave, lower frequency.
The longer the wave, the lower the frequency. Wonderful, right? That means that frequency would be what? Inversely proportional to lambda?
Yeah.
Alright. And we already know the frequency, right? So IR would be, X-rays would be the highest frequency and IR would be the lowest frequency. So we know that already. So what is happening here? Compare the frequencies and the wavelength and put them where you need to put them. So P would be in what range? Low frequency.
EBIR.
Should it be IR? So we have IR and then Q would be what? Viz? Or sorry, it can't be Viz. UV?
Yeah, UV.
Alright, and then the other one will be radio or X-rays.
X-rays.
Alright. That's fine so far. Which of the following processes occur in a mass spectrometer before isotopes can be detected?
1 and 3.
1 and 3. Wonderful. Amplification speaks to the manipulation of the rays being used generally within the what you'd call it ionization step, right? So amplification can refer to that as well, and it can be used to, it could be referring to the amplification, right, of the readings to produce a graph. So it's kind of vague amplification, and we know that amplification is not a word that appears within the processes in the mass spectrometer, so it should stick out like a sore thumb, so it should be fine. 26, I'm talking about 36. In the mass spectrometer, a molecular ion is formed from a compound by the, what is the molecular ion
C.
peak? Okay, C. What is the molecular ion peak characterized by? M plus, right? So if the molecular ion peak is characterized by M plus, and plus is a positive charge, it must have lost an electron. Alright, so we have that there. I just want to make sure that you guys have something to attach the questions with rather than just saying A, B, C, D. Right, what transitions are expected from this wonderful compound that we have here in a UV spectrum? What compound is this, first of all? Which compound is this?
Is it nitrobenzene?
Wonderful, it's nitrobenzene. Right, so you know the different structures in it. So tell me what's happening.
I'm thinking C.
Right, so you're thinking C. You're thinking correctly. So we know that nitrobenzene is aromatic first of all. That means that double bonds must happen. Therefore, there will be pi to pi star and N. Well, we know that that's pi to pi star. Give me. Okay, never mind. So it would be pi to pi star. Right. For the nitronium ion, right, when that bonds to form the nitrobenzene, we know that that will have free electrons on the oxygen, right? So notice how they're combining two different sections of the syllabus together, and that's what chemistry is all about. We don't just learn everything separately and we just go both ways. Everything combines. So we know that there'll be free electrons on the nitronium group, right? Or the nitrile. No, it's not a nitrile. Right, on the NO2 group. So there must be non-bonding electrons. Therefore, there can be non-bonding to pi star and non-bonding to sigma. Right? And we can note that because on the nitronium group, there's also a double bond and a single bond. Right? So everything can occur here. So we have that. 20, somebody saying something with your mic on? Alright. So the compound X contains three components P, Q, and R. Compound P is needed as a starting material in the synthesis of a new drug. Which of the following methods of chromatography is most suitable for obtaining a pure sample of compound P?
I'm thinking between A and C. I'm not sure on which ones.
A and C, alright. You know what is gas liquid chromatography used for? Note the amount of things within compound Y, the amount of components. Can gas liquid chromatography separate three different components into its purest form? Or can it only separate one within gas and one within liquid, allowing it to be different? It's similar to that of, I think it would be similar to that of simple distillation, in which simple distillation makes the most sense for separating two and only two substances, where gas liquid chromatography would be best for separating two as well. That's my opinion. What do you guys think?
What I read, the column chromatography is more used for purification in a sense. But I was thinking that the gas liquid is mostly used for forensic testing. Like, can't really separate it that much. Because if the gas, I'm not sure, but I just thought that a gas liquid is mostly used for forensic testing. Not really a purification method.
Yeah, so it can be used for, it is purer than that of thin layer on paper, which won't really give you anything, right? But column would be purer than that itself, right? because gas liquid gives you some amount of the components for forensic testing, as you said, right? And other types of analytic purposes, right? But column would be the best bet, right, for your pure sum. It won't be the best, but best bet. So, well, I mean, out of the chromatographies there, then it would be the best. 29. Which of the following bonds would show the strongest absorption in the IR spectroscopic analysis? What governs this? What concept governs the strength of absorption in IR?
Polarity of the bond.
Polarity. And which one has the largest polar difference or polarity difference?
D as in dog.
Hydrogen and oxygen, and that's why you say 3000 would be OH group, right? So it's a large absorbance from the OH groups coming down. So if you even have no idea what's happening here, your data booklet should contain some of these wave numbers, and the higher the wave number, the higher the absorbance. So you can just connect the dots and you get the answer. If they give you a different array and you don't really and you're not really sure, right? Or if you want to confirm, you can use the data booklet. It takes 5 centimeter cubes of 1.4 molar sulfuric sodium hydroxide to neutralize 150 centimeter cubes of hydrochloric acid with an unknown concentration. What was the original concentration of the acid back titration? What do we do here? Well, I mean, it could be, it's a titration. Let's just say that. What are we doing here?
Well, you can start off by writing the balanced equation. So NaOH plus HCl to give NaCl plus H2O. Then you realize that the mole ratio between NaOH and HCl is 1:1. So by finding the number of moles of NaOH, we can find the number of moles of HCl. And number of moles is equal to concentration times volume.
Mm-hmm.
And then we find the number of moles of HCl, we can find the concentration because we have the volume.
So the number of moles of HCl would be the same number of moles of sodium hydroxide, so you just divide that. Alright. So that's a wonderful... What is happening with my... Give me a moment. What is happening here? Let me fix all of that. Sorry about that. Because I was writing all the while and realized that nothing was on the screen. It messed up. So 1:1 ratio, right? So we're saying after we get the number of moles of sodium hydroxide, it should be the same number of moles of HCl. And all we do is divide that by the volume that we have, right? So what is going to be the working? What is the concentration of NaO? Well, it's the number of moles of NaOH, I mean. Moles is equal to what?
Concentration times volume, so 1.4 times 0.005. I don't have a calculator.
Alright, no worries. We have around 29 persons left, so one of the 29 persons must have a calculator. What's the answer? What's the answer, guys? Let me draw for a calculator there.
Oh,
on
my calculator. It's 7 times 10 to minus 3.
So 7 times 10. This sounds really familiar. It's the minus 3. Alright, and that would be the number of moles of sodium hydroxide. So 7 times 10 to the minus third power. And that would be a 1:1 ratio. So we know that this would be 7 times 10 to the negative third power. Right, that means that for the concentration, we just have moles over volume. So we divide that by what? Thank you, Mom. Alright, thank you. Alright, so what would be the answer for this? What we're dividing it by?
The 150 divided by 1,000. So your final answer should be 0.047.
150 divided by 1,000. Right, should give you an answer. Let's just call this x and then we divide x by that. What would be the answer? What would be the final answer for the question?
Oh, 0.047.
0.047. Right, it's just in interest of time, right? For anybody rereading, they'll figure out where they get x from to divide. And that's because of the conversion from CM cube to DM cube, right? All right, give me one moment. I'm just organizing some lectures from organic chemistry to make sure that I have them. All right. Okay, so I should be able to move on now. Let me just do that later. Alright, a sample of crude oil contains mainly the whatever that is, right? What is that molecule? Somebody name it. Put a name to it, please.
The octane?
Is it well, I don't know, Mr. Jardine. Cape Unit 2 student. Is it?
Yeah, I'll go with that.
Alright, okay. So you'll go with that, right? So we have 8 carbon. So, well, if it's 8 carbon, it's probably pentane, isn't it? Alright, so let's look at this, right? So, in which crude oil fraction would you expect to find this sample? This is a CSEC question as well, you know. I saw this on a CSEC paper. CSEC paper 2 albeit, but okay.
Naphtha and gasoline?
Naphtha and gasoline, interesting. Everybody
Wait,
else agree? Go ahead.
isn't it D?
Isn't it B as in boy?
Oh, D as in dog.
Or refinery dog? Refinery gases. Alright. Not really refinery dogs. Refinery gases. Those would be usually the ones of the low molecular weight, right?
Yeah, I can't remember which one is like 4 carbons to 8 carbons.
4 to 8. But the refinery gases would be around 4 to 8. So it makes sense. Refinery gases would be around 4 to 8 for real. And then after that, now you have 8 to around another number to give you the kerosene. No, it would be giving you naphtha and gasoline. I don't think naphtha and gasoline should be that close, but around that. And then you'd have kerosene and bitumen, and then bitumen only. So do we agree with refinery gases being the answer? What would be the answer? Anybody else would like to second it? I need a second opinion. Go ahead.
So this is like so confusing because the CSEC would have you, as you say, 4 to 8, and then the CAPE would say 1 to 4.
Oh, so what does the CAPE say about 8 carbons?
So about what?
What does CAPE say about 8 carbons? Where would CAPE place it?
Somewhere in between naphtha and gasoline, thereabouts.
Alright, naphtha would be naphtha would be more complex than gasoline, right?
Yeah, I'm looking at this textbook right now.
Go ahead.
It says gasoline and naphtha is from 5 to 10. So the same. Refinery gas is 1 to 4.
Okay.
Kerosene is 11 to 8. So
Okay, I think C may be the better answer. Alright, because a lot of concepts change from CSEC coming into CAPE, so I think that would be the better answer for real. Because based on it, the refinery gases would be the small ones. That's why I really asked whether or not, the refinery gases would be like your propane and your butane and your methane and stuff like that. Well, most likely propane and butane. And the one with the larger molecular weights would be around the naphtha and the gasoline, then kerosene and bitumen, then bitumen only. So I think it's naphtha and gasoline would be the better answer, based on the evidence provided. 32. Which of the following factors is least important in locating a company where iron is extracted from its ore? Which is the least important?
B, as in boy.
Okay, closest to the market. Okay. Everybody else agrees?
I agree.
Okay. So we have that there, closest to the market. So we have that there. So from the reaction given below, a high pressure would give the best yield, but in industry, a moderate pressure would be used, right? Why is a moderate pressure used in industry rather than a high pressure?
A. It's too expensive.
Alright, way too expensive. Alright, so we have that there. Okay, so let's look at this 31. Which of the following, what is the most appropriate inference based on the above observation?
A. Lead
A,
ions.
lead
Yeah, I'll
ions.
go with A.
Alright, so we know that that's supposed to give. Oh, alright. Because that should be an insoluble salt. Alright, so that makes sense. Insoluble salt should form. Seems fine. Alright, so let's look at this now. What would be the answer for this? What is the product of the following unbalanced equation? The valency of aluminium should allow you to get this. The valency of aluminium is 3 plus, right? And OH is negative. That means that you need 3 OHs to balance that, right? So some persons tend to just start to immediately overthink the entire question, right? They're like, this is too simple, so there must be another way, but it's not true, right? C could be taken, but the fact that C is not in its lowest whole number ratios, right? It gives some amount of speculation to that, right? You would like to simplify everything, right? So the simplest is usually the best thing we work with. 36 refers to the manufacture of chlorine by the electrolysis of brine using diaphragm cell. The anode it's made up of.
Yes, enough.
Titanium with an inert coating of ruthenium oxide. Where's Ruth? I'm joking. That's a really corny joke I was about to make, so I stopped myself.
Graphite.
Alright. So somebody said titanium with the inert coating of ruthenium. Cleon, why did you say that? Hello? Okay, is it graphite or is it titanium with the coating of ruthenium oxide? Or some people like to say ruthenium instead of ruthenium, but yeah. What is the answer?
I think it's
D
D.
as in dog.
Okay, I'm hearing D and I'm hearing B. Two disputing answers. Alright, so
D as
let's.
in
Yes. Okay, so let's look at the diaphragm. Let me just bring up a diagram of it right now on the screen. Right, it's called being lazy. So let me just see if I can bring up one real quick. Why is it going to private state? What is this? Brine extraction. Let me just put brine. So let's see what's happening here. Images of the structure. I hope it gives me a diagram and doesn't give me like a whole factory view of what happens. Alright. So we're saying here that we have that. The anode, where's the anode? Alright. Where it gives us the material. What do you guys say the material was made out of again? The anode? Was graphite or the titanium, right?
Graphite.
Alright, so I was saying that somebody said titanium and somebody said graphite. So I'm just looking at it to make sure that whatever we're saying makes sense. Would be a cathode. And the cathode is made out of what? Think that would be graphite as well?
I think it. I thought it was steel,
Or steel. Or cathode is steel. Alright. And then the other would be.
but
Oh,
I don't. Really,
if one is alright, wait, hold on. If one is literally a piece of steel, right? For the cathode, which kind of makes sense, then the anode shouldn't be graphite. Because if you think about it, right, looking at your EMF values, right, Unit 1 chemistry, sorry, CSEC chemistry, right, shouldn't it just make sense that the other one should be one that has a lower, what would it be now, lower reducing power?
I don't know. I'm just guessing. Because I remember reading something about.
Sir, could you go on one of the diagrams?
Oh, one of the diagrams. Give me a second. I was just gonna Google it. Let me see. This is a diagram. So we have that there. It doesn't.
Someone can check the study guide.
Give me 1 moment. All right. I'm back. I genuinely don't remember the answer for this though. Alright, I genuinely don't remember.
I just checked the textbook and it said titanium anode.
Ah, okay. So everybody who said?
What about the cathode?
Oh, what's the cathode? Yeah, what's the
So the
cathode?
cathode is a steel. It says the cathode is steel.
Alright, hear that, Ruth? Ruth over here. Alright, that's why I make Ruth here. So the answer should be D. Alright, chlorine is most widely used for the manufacture of
the screen, sir, the screen.
The screen is screening right now. Give it a second. Okay, go ahead.
Is it solvent and PVC?
Alright. Everybody else agrees?
Yeah, then boy.
Solvents, alright. And PVC. What would PVC be used for?
Pipes and them
Alright.
stuff.
Okay, so it's a type of hard plastic. Interesting. Alright, so which of the following methods are used in water purification?
Wait, sir, actually correct.
It's fine.
Okay.
I'm yet to see why we have the production of sodium chloride generally. So yeah. Which of the following methods are you know that you can use never mind, let me not answer that. Which of the following methods are used in purification of water? Would it be all of them, right? Right? Filtration for the immiscible, distillation for miscible, and UV radiation for the living materials within the water. Why that's living material? Whatever. The living organisms. But saying living organisms is kind of redundant because organisms are living. So okay. 39. In which layer of the atmosphere is ozone detrimental to human health and vegetation? What would be the answer?
C.
C would remain as the troposphere. You guys sure that it will remain as the troposphere?
Yeah.
Alright. In which of the steps involved in the manufacture of sulfuric acid and sulfur that go ahead? Somebody raise their hand.
Wait, I remember my teacher mentioning like another layer of the atmosphere as it relates to like ozone though.
Yeah, that's what I'm asking if you're all sure, but like, I'm not sure, and I think I'm allowed to make mistakes. So I'm not sure about that because is it gonna be the same thing? Because the troposphere would be what layer of the atmosphere? Wouldn't that be like far away from human inhabitants? So why would that affect our health?
That is the closest one.
That would be closest for real. Wait, the biosphere would be well, I mean, out of all of them, I guess the troposphere would be a bit closer than like the thermosphere and the mesosphere, and the stratosphere is definitely not the closer one. Oh yeah, for real. All right. So based on the closeness to the biosphere, I think it should make sense. And you guys learn about biosphere and stuff like that in biology, so it should be fine. In one of the steps involved in the manufacture of sulfuric acid, sulfur dioxide, and oxygen are mixed to form sulfur trioxide according to the following equation. Which of the following options describes the effect of adding the catalyst, vanadium oxide, to the mixture? So what does a catalyst do? So catalyst is going to affect the rate, so we can have that. Right, will it change the equilibrium?
No.
No. Okay, B. Chlorine can be produced by the diaphragm method and mercury cell electrolysis. Which of the following statements is or are true regarding the diaphragm cell method?
So this one I'm having like mixed feelings about, because I know it's more energy efficient, but less harmful. I'm not sure, because mercury is toxic, but like,
Chlorine as well.
oh, I know
And
too.
it's also carcinogenic. Well, that wouldn't be, well, yeah.
Mm-hmm. Oh, so you're saying that it definitely is more energy efficient? Alright, so you're saying that. So I think it would be less harmful. Right? Because we know that they have the production of chlorine gases and stuff like that. But chlorine can generally recombine into things that are useful. Mercury can as well. But mercury is most definitely more deadly than chlorine itself. Right? Because mercury cannot only it's not a gas, right? So it can seep into soil, it can seep into animals, and then it can go through bioaccumulation. Chlorine doesn't do that. Mercury can create, metallic poisoning in the blood and stuff like that. Chlorine doesn't do that. Chlorine, of course, can kill, but the concentrated chlorine that they have, right, would be redirected in the production of something else, right? The mercury generally, right, would just be like probably the more harmful thing to the environment. Because chlorine exists within our atmosphere, Chlorine is there, having it's chill, it's fine, right? But mercury within the environment would basically condemn the entire area. So I think that it would be less harmful to use the diaphragm cell. And I think that when I was reading the study guide and the textbook, it outlined that. I don't remember which page right now, but yeah. It did speak about that. The fact that diaphragm cells should be less harmful. So I think it would be 2 and 3. Right? I think it should be less harmful, man. Because metals are usually more harmful than usually more harmful than the non-metals. Chlorofluorocarbons with relatively high proportions, right, of chlorine are potentially more damaging to the ozone layer. Which of the following reactions gives evidence of this?
Isn't boy.
B as in boy?
Yeah.
Okay, why would you state that? Because it's ripping apart ozone?
Yeah, it's showing you how the ozone is destroyed by it.
Alright, so it's showing the destruction of ozone back into molecular oxygen and bimolecular and monomolecular oxygen. Alright, so we're seeing that. Well, atomic oxygen and molecular oxygen. Alright, so I think B is demonstrating the destruction, so I think it makes sense. Which of the following is not manufactured using ammonia?
A.
A.
Yes or
Alright.
no?
So I don't see why you would use ammonia. But okay. Which of the following processes is not involved in the manufacture of ethanol? Alright, what will it be? Not involved.
Would it be B?
Aerobic oxidation of sugar. Alright. The aerobic oxidation of sugar, right? That if it's aerobic in oxidation, then we know that the oxidation creating pyruvate from glucose will occur, and then we're going to have the Krebs cycle, and then we're gonna have the ETC, right? Generally not producing anything like that, right? So I think it would be aerobic oxidation of sugar will not amount to the creation of ethanol generally, right? I think that makes sense. But like when we're looking at that's when we're looking at some of the molecules or some of the organisms that can as well be aerobically active. But when we look at ethanol production, we normally look at things like yeast and those type of stuff, right? Um, Yeast would not be able to do aerobic oxidation, so that makes it worse. Um, Plants, some persons would rely on plants for certain things for the production of different stuff. So I think plants generally can go through aerobic and non-aerobic respiration, right? But aerobic oxidation of sugar, I don't think that will amount to ethanol. Because remember, it is a secondary pathway, right, after the absence of oxygen that allows for for ethanol fermentation to occur. Right, so I think that makes sense. And thermal pollutant results in pollution, sorry, results in
See?
if the temperature of water increases, does that increase oxygen levels or decrease oxygen levels in water?
Decrease.
Decrease. Wonderful. Right? So as the oceans heat up, the oxygen level of the oceans depletes, allowing less oxygen to go through, the gills of fish, right? So fish will no longer be able to breathe properly, decreasing fish populations. Right? So you could speak about that. That's all about green chemistry and environmental chemistry. A lot of persons don't really look to environmental chemistry, but I think it's a pretty interesting field. Alright, so that was the May June 2017 paper. How are we feeling?